blue. Hello, this is Zhao Yang introducing our recent work, Predictive Coding Feedback Results in Perceived Illusory Contours in a Recurrent Neural Network. Recent studies show that feed-forward networks cannot perceive illusory contours such as this white square on top of 4 black disks. Physiological evidence suggests that the perception of illusory contour involves feedback connections in the brain. Here we ask whether recurrent feedback neural networks perceive illusory contours in the way that humans do. To this end, we use an autoencoder module where an input picture is encoded through a convolution process and then decoded back to the picture. Here we stacked 3 such autoencoders. After initialization, we use a predictive coding strategy to update the network over time steps. For example, its update is based on the top equation. In each time step, it will accept feed-forward input, feedback, predictions, its own memory from last time step, and the reconstruction error caused by its inaccurate prediction of lower level. So we minimize a reconstruction loss here. Finally, we added 2 fully connected layers and an output layer to perform a binary classification task. So we also minimize a classification loss. With the 2 kinds of losses, we therefore have 2 corresponding training steps. First, the network was pre-trained on CIFAR 100 dataset in an unsupervised way to obtain basic contours features. Then it was fine-tuned with a supervised form discrimination task to recognize basic pigment elements forming an illusory contour. As shown, we have 4 classes. All classes vary in position, size, luminance, and also noise. During fine-tuning, only square and random classes were used. So the network learns to judge whether a given class is a physical square or just a random combination of pigment. When testing, all-out and all-in classes were also used. So the question is, will the network simply classify the novel classes as random patterns of pigment, or will it perceive extra contour information? The result shows the probability of square over time steps on clear images. At time step 0, the network makes its decision only based on a feed-forward path, so it can be viewed as a feed-forward baseline. Compared to it, the recurrent feedback connections result in more illusory contours being classified as square over time. With varying levels of noise, we get a similar result, except that the network gets more confused with higher noise levels. Next, we inspect the reconstructed images from the first layer. Compared to the original noisy input, the reconstructed images were denoised by the network. We constructed a figure ground value quantity. Humans tend to see a brighter or darker figure pop out from the background, even though the luminance is the same. In the reconstructed images from the network, we compare pixels just inside or just outside the illusory contour, taking into account the expected polarity of the illusion. If the network sees the illusion like humans, the comparison should lead to a non-zero value. Again, the FG value for illusory contour is higher than other classes, suggesting the recurrent network actually perceives an illusory contour. So finally, in conclusion, we provide evidence that brain-inspired recurrent dynamics can lead artificial networks to perceive illusory contours like human. Thanks for attention.